Processes in the world around us, such as heat diffusion over a 2D plane, are described using differential equations. These can be solved numerically using a stencil on a set of finite grid points, replacing the continuum of space and time. Depending on the process, we may be able to compute many or all of the points in the stencil in parallel. The AllScale project is implementing a novel approach using recursive nested parallelism, a technique which is implemented with template metaprogramming in the C++ language, and furthermore enabled with a task-based runtime system. Traditionally high-performance computing code, or HPC as it is more often known, has used a combination of the OpenMP and MPI toolkits to execute on multi-core systems with shared memory and on distributed systems. For resilience, exciting opportunities arise with the AllScale runtime. Since it can track data dependencies, the runtime allows to implement rollback recovery mechanisms without modifying applications and are very efficient. Resilience strategies can be implemented in the runtime without application changes. The explicit data dependencies allow to explore efficient localized rollback. Consider a 2D stencil application, which is usually decomposed in subdomains. If a process and all its associated data are lost, the data dependencies allow to roll back only the minimum required processes, which hold essential data. These are shown in red for iterations preceding the crash iteration J. Note that in traditional rollback, we would recompute the entire domain for each repeated iteration to recover. AllScale takes a novel approach by using a task-based runtime. Task-based runtimes decompose the problem into communicating tasks and overcome the communication barriers well known to HPC programmers. They are the best approach for the exascale environment. AllScale uses 3 distinct applications as pilots with which to prove the applicability of recursive nested parallelism. In general, the approach to solve any problem is to develop a computational model using partial differential equations, execute it, compare to experiment, improve the model, repeat. Put another way, to feedback and improve the model. The pilot applications in AllScale are modelling of the solar wind, study of oceanography, particularly relating to oil spills, and gas flow in a high bypass turbofan jet engine. In all 3 cases, the continuum of space and time is mapped to a grid. The computation at each grid point is farmed out to recursively nested tasks managed by the AllScale runtime. Initial results are promising, and soon new science will be possible in each application domain thanks to the output from AllScale research. The AllScale project is coordinated by the University of Innsbruck and has academic and industrial partners from across the European Union. The partners are grateful to the European Commission for funding AllScale under the Horizon 2020 programme.